The chart they give us at the top is how fast the water is being pumped out of the tank. And then the equation they give us here is the rate at which the water is being pumped into the tank. Says it's differentiable, which means it's automatically continuous. So that's all good. Also gives us an initial amount of water in the tank. So I'll keep those things in mind as I'm going through the problem. Part A, r prime of 2, we know derivative is slope. And this is my r function in the chart. So r prime of 2, I'm going to say, hey, 2 is in between 1 and 3. So I'm going to jot down these 2 points, which I did right here, and I just did my slope formula. That's giving my estimated derivative, and there's my negative 120. And then the units on that, since the r is in liters per hour, that's like velocity units, how fast something's going. And so your derivative of that, your slope of that would be like acceleration units, which is those weirder like liters per hour squared. Now for part B, it says use a left Riemann sum, 4 subintervals indicated by the table, to estimate the total amount of water removed from the tank. So what we're trying to figure out here is the integral of r of t in between 0 and 8, because it just says how much was removed from the tank. And that's all I care about is the r. The r is the removal amount. Don't care about the w, don't care about what's already there. And so since we have this chart and we're supposed to approximate the integral using a left Riemann sum, let's review that pattern quickly without the picture. You start the left side of your interval, so you're going to go 1340 times the distance between 0 and 1, which is 1. So you go 1340 times 1 plus 1190 times 2 plus 950 times 3 plus 740 times 2. And that's how I'm coming up with all those numbers. Plug them into the calculator. That's going to give you the total amount of liters right there. So remember, if your R was in liters per hour, when you integrate that, that's going to drop off the per hour. It's going to give you the total amount of liters. And just for fun, let's do a right Riemann sum. I think we have that down by now, but we can practice just one more time. You start the right side of your, for a right Riemann sum, which I did not ask for, but we're going to practice that. You start the right side of your interval. So you're going to go 700 times 2 plus 740 times 3 plus 950 times 2 plus 1190 times 1. So hopefully you just did that in your head with me together, and you got that same thing that I got. Now, when it does ask, is it an under or over estimate? So it'll ask us on a left Riemann sum and a right Riemann sum, typically not a midpoint Riemann sum, because half the rectangle will be above, half of the rectangle will be below on a midpoint Riemann sum, and trapezoid is just too close to tell. But on a left or right Riemann sum, they could ask us this question: is this answer an under or over estimate? And that's when I look at these values. I notice that they're decreasing as I go left or right. And so if those are decreasing, that means my function is decreasing. So I'm just going to draw a decreasing graph real quick and do a left Riemann sum. That means if I were to draw a picture, I would start at the left side of the interval. I would draw it up to the curve and then draw the height over. And then I go up to the curve, draw the height over, up to the curve, draw the height over. And all those rectangles are going to be above the curve, which gives us an overestimate. But they don't want to hear the reason because the rectangles are above the curve. You got to tell me what that function is doing. So you guys say overestimate since the R is decreasing. Letter C, I kind of like this. Sometimes we're faced with problems that are a little bit harder than this, but this total concept right here, it says find the total amount of water in the tank to the nearest liter. So I don't need to worry about 3 numbers after the decimal place. But if I want to find the total amount of water in the tank at the end of 8 hours, that's when you need to take into account everything. You got to take into account what was already there. You got to take into account how much water entered the tank in those 8 hours. And then you got to take into account how much water left the tank in those 8 hours there. So that's why they told us that t equals 0. We started with 50,000 liters. So I got that taken care of right there. And then when I integrate the W of T, that's how the W is how fast the water is flowing into the tank. So when I integrate the W of T in between 0 and 8, this expression will give me how much total water entered the tank in those 8 hours, okay? And then that's gonna be a math 9 function with that function there. So math 9, that sucker, to get this 7836 number. Now it does say like 0.195, but it says to the nearest gallon. So that's why I'm not rounding to the 3 numbers after the decimal on this one. And then we're gonna subtract out the integral between 0 and 8 of the R of T. That's the expression that's gonna give us the total amount of water that left the tank in those 8 hours, which we already calculated in letter B was at 8,050. And then so just put that to the calculator, and then there's your total number of liters at the end of 8 hours right there. The last one is going to involve a theorem, because it says, is there a time when the removal rate is the same as the entering rate? And so they want to know, is the W equal to the T at all? Now, I have a more precise way down here that I'm going to talk about first. But when I first worked out the problem, I was kind of reasoning out like this. Let me just talk about the precise way first, and then we'll kind of mention that. But they want to know when is W equal to R, or if there, and then I know I'm using a theorem on this just because it says, does there have to be a time? Does there must be something? Does there have to be something? That's when I start thinking about theorems, because theorem guarantees that something has to take place there. So that's why I'm even thinking about a theorem to begin with. Now, if I want to know is W equal to R, you know what we could do? We could subtract stuff to both sides. That's if W minus R is equal to 0. Now, if I'm trying to figure out if something is equal to 0, this is what we're going to use as the intermediate value theorem. The intermediate value theorem says if you have a continuous function and two different y values, so if you have a y value down here and a y value up here, if you have a continuous function, it has to cross through all the y values in between. And then if you want to, you could use that really easily to find zeros. Like if you have a function, if you say it's continuous function, and then if they tell us that we have a y, or if we could find that we have a y value down here and a y value up here, like a negative y value and a positive y value, then to get to one to the other, you had to cross the x-axis, which means you have to have a 0 right there. And if you have to have a 0 right there, that's what we're talking about right here. Does this thing have a 0? So all I did was take the endpoints, that's the 0 and the 8, and I did W of 0 minus R of 0 and W of 8 minus R of 8. So I'm just plugging in 0 for the t's into this function right here. And then so the W of 0, W of 8, I had to plug into this function. And then the R of 0, R of 8 was the 1340 and the 700 right there. And here, see, I got a positive answer and then a negative answer. So think about it. If you have a positive answer and a negative answer, and all that stuff is continuous there, that means you have to cross the x-axis, because, and you have to have a 0 there, because to get from a positive answer to a negative answer, you're going from above to below the x-axis, and you have to cross the x-axis there. So the intermediate value theorem is going to guarantee that. Now, when I very first worked this out, and this would have been just fine as well, but I thought, okay, is W equal to R? And then I just took the endpoints and I plugged in the 0 and the 8 for the W function to this equation up here, and I got 2081.52. And then I know by looking at this equation, your e to the x graph is a continuous function. We don't have to look at the pen when we draw that thing. So I mentioned like it was continuous and differentiable. It was smooth and curvy there, right? But, and then what I noticed, okay, if my W graph was going in between 81 and 2000, and I noticed the chart numbers went from 700 as a min to 1340 as a max. So I said that entire range of the R was in between the 81 and the 2000, which means they have to cross and they got to be equal to each other at some point. You know, when you're going from when you're going from 81 to 2000, you're going to hit all those values right there. So at some point, they're both going to be 800, or they're both going to be 1200 and stuff there. So they're going to have to be equal to each other. But the bottom line is, when you want to say that something's in between something else, throw the word continuous in there. Mention what the y values are equal to, you know, because that's what that theorem says. It says if you have a continuous function and f of a is not equal to f of b, then there's a spot where that y value is going to be equal to something. And so then you just jot down that intermediate value theorem there. A grove.